Yeah, just to be a little bit random, I'm gonna start the stream an hour later. No, no, I'm kidding. As I mentioned before, I'm working on trying to get a math club together in my neighborhood, and some people have been expressing interest. So I'm like, let me. Well, I got 10, 15 people in the local area around me that responded to a Craigslist post. And you just don't. I mean, you post something on Craigslist. I mean, you're not gonna invite the people directly to your house because, I mean, you don't know. You know. And I've tried to express to the people that have been responding to me, like, hey, let's meet up online. I'm not really getting them, but I'm gonna. You know, I'm actually, when you're responding to a Craigslist uh, post, you're using the mail relay, so they give you this big gobbledygook kind of proxy email or whatever. And I've been doing a blind carbon copy to all the people that answered because it got, it's more than 10 of them, so it got too cumbersome to answer one by one. Um, I don't know if it works. If you essentially try to group email the Craigslist um, on a blind carbon copy, maybe it's not going through because I'm surprised that I have like 12 or something people that were writing me back and forth individually, but they haven't been responding to the group email. But I don't care. I'm gonna do some math. Yesterday, and what we're doing is kind of working on chapter 12 of the 8th edition of Salas-Hill Etgen's calculus of one and several variables, I think. Um, yeah. So yesterday, when I did the stream, what we were doing was developing a distance formula, and if you go back, it may not be on my YouTube channel yet. I think I was on the brink of sending it over there, but it's gonna be there soon. You can see it, but you know, uh, for just a line in the plane, just as a quick review, a line in the plane, right? We can derive a distance formula. Let me give an example here. Right. Here I am in the XY plane, and I have a right triangle, and I'm interested in the straight legs of the triangle because I'm going to try to get a formula for this distance. Well, this is the first x value that I come across, and this is the second x value, and this is the first y value, and this is the second y value. So since a squared plus b squared is equal to c squared, we could call this A and this B and this C. And we can see that x2 minus x1 equals A. And y2 minus y1 equals B. All right. So the C is the distance. Square root of c squared, I could say, because we have this a squared plus b squared equals c squared. But this means that I've got the distance between these 2 points to be equal to the square root of the sum of x2 minus x1 plus y2 minus y1 squared, right? This is the Pythagorean theorem. All right, so what we did yesterday is we did an exhausted graphing out and derivation of the distant formula for some arbitrary points in three-dimensional Cartesian space, and it turned out that uh, like if we're going to R3, put two little arrows here, then we're going to have D is equal to x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And like I was saying yesterday, you kind of imagine that's what it's gonna come out to be. And but we did it with two right triangles. We started with a right triangle in the plane and projected that triangle to the z sub 1 plane, right? And then we ran off the hypotenuse of the projection from the plane to the z1 plane. We ran off the hypotenuse of that triangle projection. Uh, 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 the uh, uh, the second right triangle to extend the top end of that triangle into three-dimensional space, and then we derive this distance formula. And after all that, I don't know, a half an hour, it comes out. Yeah, I'm still here. It's beeping me. After all that, it comes out, and um, this is what it is. All right, so we're picking up from there, and that distance formula we called 12.1.1, and then we said, we're going to say, right, the sphere of radius r centered at P naught ABC, where A, B, and C are order triples from R3, is a set of all points P of X, Y, Z with the distance P to P naught equal to R, and R usually stands for radius. We can obtain an equation for this sphere by using 12.1.1. So we just substitute a fixed point for our initial point. All right, so let's see. The sphere of radius r centered at P naught A, comma B, comma C is the set of all points P, X, Y, Z. These are the variables, right? With D, P, P naught equal R. With D from P to P naught equal R. And we're going to write that equation to be, say that this implies the equation. X minus A squared plus Y minus B squared plus Z minus c squared equals r squared. So, say A, B, and C are 0. That's going to be a sphere centered at the origin with radius r. So we have this, and we have let A, B, C equals 0, right? And we're going to have x squared, or then we'll have x squared plus y squared plus z squared equals r squared. And this may kind of be reminiscent of algebra when you did your conic sections and stuff. The equation for the circle, right, is the x squared plus y squared equals r squared. Now, I'm going to go, I'd like to get this, say I take a circle in the plane centered at the origin. And this is a familiar diagram from trigonometry and stuff, right? We get these triangles, right? As we rotate through some typical subdivisions of pi, right? If r is 1, unit circle, r equals 1, right? We know that going around this circle, or we're supposed to know, that the distance around a circle is 2 pi times the radius. I think, and I'm just, trying to revive the memory or whatever. If you take the distance around the circle, you can do this. You can try it. One way you can do this is like with a can of beans, right? Get yourself a Sharpie, get yourself a big can of beans, right? And stretch the string across your where your diameter of the can would be, the circular diameter of the can, right? And put a Sharpie mark. And you can do it in 2 colors because you want to remember the circumference versus the diameter. So you've got a diameter there, and then you wrap the string around the can, right, and make a mark where the string hits the full circumference. And then you take that string and lay it out flat and measure it with some measuring device. Calipers would be really nice, like if you had those from physics lab or something like that. Some way to make a real accurate measurement of it. And take C divided by D, and you're going to get something close to 3.14, right? All right, now I'm just trying to get towards this circumference. We're talking about the circumference is 2 pi times the radius. In the case when the radius is equal to 1, it's just 2 pi. All right, so we can experimentally, there are ways to do this, like with infinite series and, a multi-sided polygon that's first a triangle, then a square, and then a pentagon, hexagon, septamestagon, and when the number of sides gets longer and longer, the measurement of the total number of sides is going to approach the number 3.14159, or pi. There was a guy that was sent, the countryside, and his dad sent him off to college. And he came back and said, well, what did you learn in college? He said, I learned pi r squared. And his dad beat him up. He said, that's stupid. Everybody knows pi are round. And so the farmer was confused. He didn't understand that he was talking about a Greek letter, pi, which is used to represent the ratio of the circle to its diameter, right? And I think that's one of the simplest ways you can think about it. Anything that's circular, right, has a diameter. And if you take in your numerator the distance around it, and you divide it by the distance underneath, it's about 3 to 1, right? 3.14, right? That's all pi is, right? And we use a Greek letter to represent it because we don't have time to write all those infinite non-repeating decimals out. But with this formula here, let me give myself a little bit more space. I've got C divided by D, and that's equal to, and I'm going to give myself a little bit of space, pi, right? So I could multiply both sides of this equation by D. Now D divided by D here is going to cancel out, and I've got, this is going to give me that C is equal to D times pi. Well, since D is equal to 2 times the radius, right? The diameter is all the way across the circle. The radius is half of that, right? So D divided by 2 is equal to R, or D is equal to 2R. So I can substitute this in my formula here, and I've got C is equal to 2, and I like to put pi first, and then R. See, the circumference of a circle is 2 pi R. So in the case of the unit circle, I go from 0 here, and I go around the circle like one of those radar things that's going around. And it's all in increments of pi, and we end up on 2 pi. Now, if you just remember, I don't remember. No, it's 30 degrees, pi over 6. Pi 6, and then pi over 4, and then, so you subdivide the typical angles that we use that are kind of nice when we're going around the circle, increments of pi, are pi over 6, pi over 4, pi over 3, and pi over 2, right? And all the the multiples of those basic fractions. So picture in your mind the set of all these triangles. There's infinitely many triangles you can inscribe inside the unit circle. All right. So if you want that to sweep around, you can let all those calculations of x and y coordinates be calculated. The sine of an angle is the ratio of the side of the triangle opposite the internal angle here. The ratio of that to the hypotenuse of the triangle. And since the hypotenuse is 1 on the unit circle, then the sine is just this distance, right? So if I let sine and cosine sweep through all the different angles, this, instead of just having a bunch of discrete triangles, I'm going to have a point that's going to travel in a circle. Right? That's going to travel in a circle around this. And now, what I'd like to say, I kind of, people are like, this guy is ADHD. Yeah, I am. But I know where I am and why I went there, and now I'm coming back to this formula for a sphere. right? So we derived this formula for a sphere using in three-dimensional space, right? And now, we could take we could rotate the XY plane in any direction and rotate around a circle defined by any plane, right? And so when you have all those points, a set of all those points, it's going to eventually form a circle, not a circle, a sphere, a globe, right? It's going to, though the set of the totality of all those points is going to be a sphere. So what you do in your mind is you're like, okay, I can see how this point is going around in a circle, right? Well, if I rotate this unit circle on this axis 90 degrees and it's sitting then like this would be xy, and so this would be z coming out. If I rotated it up, I'd be looking at a circle in the xz plane, right? And instead of having uh, uh, x squared plus y squared equals r squared, I would have, in that case, x squared plus z squared equals r squared, right? Now, I could then take that circle again and rotate it to where it's on the y-axis, and then I'm looking at the yz plane, and I can get a formula for a circle in the yz plane, and of course it's going to be y squared plus z squared is equal to r squared, right? So if you imagine, rotating everywhere, right, all the way around 360 degrees, around 360 degrees, it's going to be the set of all points that's going to form a sphere. All right. So I just like to say that because it makes me feel more like we've been a little bit thorough. I'm gonna draw my coordinate system here, and the z-axis. In this particular book, uh, we have this convention of having x coming out, and then the positive y-axis going this way. And so, mm-hmm, mm-hmm. I'm trying to get an idea of what would be a good place to draw my sphere. Now, um, that's going to be my radius. And I'm going to go down into the plane here. Say it's up above the plane. And I'm going to have this to be point B. And this to be point A. So here I'm going to have A, B, 0. A sphere centered at this point, would have this, right? And but if I project it up, it's gonna be see. This is A, B, C. Woohoo! All right,
So,
there's my daughter. Hey, come here.
so it's April Fool's Day.
Is it April Fool's Day?
Yeah, so follow me.
Okay. All right. Well, ladies and gentlemen, my daughter is calling. Uh, uh, yeah. Let's see. I'm gonna try to be back in just a moment. April Fool's Day. How's she got that? It's fantastic. All right. I am gonna have to let me turn back on here. Unfortunately, I'm gonna have to drop off, and the thing is, my my daughter wanted to prank me some kind of way. I'm not sure what, but she had like an open container of rubbing alcohol, and I just kind of picked it up, and I was like, well, this is kind of dangerous, we want to close it or whatever. And now she's crying because I spoiled the prank or whatever. So I need to be a good homeschooling parent and go take care of her emotional crisis that she's having. But thank you for tuning in, and we made it a little bit further into our endeavors in vector calculus, and I hope to see you again soon. Take care. Goodbye.